In this video, we will introduce the concept of minimum potential energy to calculate equilibrium displacements for one-dimensional axial force elements. To begin with, we illustrate the description of our system. This is a bar, supported from underneath, subject to some external load, and a system of internal axial forces. It has a single coordinate denoted by x, and it is discretized into a number of elements. For illustration purposes, I've chosen 3 elements, and corresponding node numbers 1 to 4. The displacements at each node are labelled, and we use the letter U to describe these. The idea behind the minimum potential energy formulation is that the equilibrium state of our system can be found by minimizing its total potential energy. For a stable system, we can draw what the potential energy looks like with respect to a displacement parameter U, the character capital Phi here represents the total potential energy. For a stable system, total potential energy tends to have a downward slope, and if you were to draw a ball running down this slope, it would always tend towards the center. The equilibrium is where this slope is equal to 0, and we say that this occurs at a value U star and a corresponding value of total potential energy of pi star. More formally, we say that the equilibrium occurs when the first partial derivative of the total potential energy with respect to our state variable, which in this case is displacement, U, is equal to 0. To use this method, the following must be satisfied. Firstly, compatible displacements from one element and another are said to exist. This means that the first derivatives across each node must be continuous. All boundary conditions must be satisfied. The total potential energy equation must be written in terms of unknown displacements. And finally, the total potential energy is minimized with respect to unknown displacements. To begin our analysis, we write down the general expression for total potential energy as denoted by capital Pi. That equals lambda minus W, which is equal again to lambda minus P times by U. Lambda in this expression is the strain energy. W is the work done by the load. And then we say that W is equal to P times U, where P is the applied load U is the displacement caused by the load. It's important to note that the applied load and the displacement caused by the load both operate in the same direction. For the system of elements, the total potential energy is the summation of the strain energy and all the work done by all the external loads and their corresponding displacements. This means that equation 1 is rewritten like so, where we sum over the elements, which we denote by E, from 1 to n, and we also sum by all the external loads, I, from 1 to P. The next step is to come up with an expression for the strain energy. In general, the elastic strain energy for an element deforming in the x direction is given by the following expression. Capital lambda E is equal to the volume integral of the stress in the x direction multiplied by the strain in the x direction divided by 2 and integrated with respect to the volume dV. The elastic strain energy for an axial element can be visualized as the area under the stress-strain curve. We can draw this where in this case we've got strain as our x-axis and stress as our y-axis. Picking two particular values of stress and strain, epsilon 1 and sigma 1, then the strain energy in this case is simply the area under the curve. This explains why we integrate this product. In this course we want to be more general, so for now we will continue to represent strain energy as shown in equation 3. Returning our attention to equation 3, we note that for the stress sigma xx that it can be written as a function of the strain, where we multiply our strain by the modulus of elasticity, essentially invoking Hooke's law. If we substitute equation 4 into equation 3, then we get the following expression for strain energy. Lambda E is equal to the volume integral of the modulus elasticity multiplied by the strain squared over 2 with respect to the volume, or it can be written the other way around as the integral of the stress squared, again with respect to the volume. To obtain the nodal displacements in our system, we must evaluate this integral. Let us now focus our attention on a single element. This element has two nodes, I and J, and corresponding displacements UI and uj. The overall length of this element is given by L, and it has properties of area, modulus of elasticity, thermal properties, and internal element forces, which we denote by Fe. These are different to the applied forces. This element has two nodes and 1 degree of freedom per node, denoted by U. Because it only has a single degree of freedom per node, we refer to this as a one-dimensional element. To proceed, we must now rewrite the strain energy in terms of displacements. Firstly, we begin by writing down an expression for total strain. We denote this by EXX. And this is just equal to the engineering strain plus the thermal strain. We can then rearrange this to make the engineering strain the subject of the formula, giving us our total strain minus our thermal strain. We define the thermal strain in the following way. Epsilon T is equal to alpha times by delta T, where alpha is our thermal coefficient and delta T is our change in temperature. Substituting equation 8 back into our definition of engineering strain, we get epsilon xx as being equal to du by dx minus alpha delta t. In this case, you'll note that we've expressed our strain in terms of displacements. And this follows naturally from the engineering definition of strain, which is basically the change of length over a given length. We now substitute equation 9 into equation 5, so we get an updated version of our elastic strain energy. So lambda E now is equal to Young's modulus over 2 multiplied by the volume integral of our strain definition all squared and integrated with respect to the volume. We can then expand this expression out to get the following: E over 2 times by the volume integral of one of our strain measures squared and the other terms. We note that the elemental volume, dV, can be expressed as the product of an incremental area and an incremental length. That is to say that dV is equal to dA, the incremental area, times by dx, the incremental length. Because the area is constant along the length of the element, we can say that generally, for the volume integral of a function f of x, the integral v f of x with respect to the volume can be rewritten as the integral over the length and the integral over the area of f of x with respect to the area and the length. And because, as we said before, the area is constant, that can move outside of the integral to give us the area multiplied by the integral over the length of the element of f of x dx. Using the information we've obtained from equation 12, we can now say that equation 10 takes on the following form. Lambda E is now equal to the area times by the Young's modulus over 2. Before we just go on, we just have a look again at equation 10. We can see that before it was just the Young's modulus over 2. Now it is the area times by the Young's modulus over 2. And we are now replacing the volume integral with an integral over the length. And then we're keeping the other term the same, the strain, but squaring it as before. And we're now integrating with respect to dx. We can do the same procedure with the next term, where instead of the volume integral, we now have E times by the area times by alpha times by the temperature change. And this time we're integrating over the length. And we're doing this with respect to dx. The final term is manipulated in the same way. This time we have E times by A times by alpha delta t, all squared, divided by 2, and then we're just left with the integral of the length with respect to dx. This is equation 13. We have now reduced the problem to a one-dimensional integral with respect to x. So far we've obtained an expression for strain energy in terms of continuous displacements u. Which we denote by lowercase u. Because we are working with the discretized system, we need to express the strain energy, lambda E, in terms of nodal displacements. Which we denote as capital U. To do this, we revisit the displacement approximation equation that we derived in the previous video. We recall that this was defined as lowercase phi equal to capital Xj minus lowercase x divided by the length of the element times by the nodal value of phi I plus lowercase x minus capital Xi divided by the length of the element times by the nodal value of phi at node j. For axial elements, the term phi is the displacement coordinate u, lowercase u. Accordingly, capital phi I becomes the nodal displacement capital Ui, and capital phi j becomes capital J, capital Uj. Thus, Our displacement approximation equation can now be rewritten as lowercase u being equal to capital Xj minus x over L times by capital Ui plus x minus capital Xi over L times by capital Uj. Capital Xj is simply a nodal value of lowercase x, which describes the position of the node in the system. The strain measure that we defined previously has been written as du by dx. In order to proceed with this, we need to convert this into nodal values. If we plot out a representative element, we can see how this can be achieved. We have our continuous value of x as well as our nodal value of x along the horizontal axis, and our continuous value of u and nodal value of u on the y-axis. If we now just draw one of our elements in a displaced configuration and mark out its coordinates, so the first set of nodal coordinates at node I is ui and capital Xi, and at node j our coordinates are capital Uj and capital Xj. The slope of this line in continuous coordinates is given by du by dx. By looking at this diagram, it should become clear that the derivative du with respect to dx over this element can be written in terms of nodal values. Capital Uj minus capital Ui divided by capital Xj minus capital Xi. We can then rearrange this so that it's written as minus Ui plus Uj divided by L, where L is the length of the element, and that's simply equal to Xj minus Xi. As the value shown in this equation, equation 16, is constant, noting that it does not contain a lowercase x, it can be placed outside of the integrals in equation 13. If we now rewrite equation 13, substituting in for what our new value of du by dx is, we get the following expression. Lambda e is equal to ae over 2 times by du by dx squared times by our integral from 0 to L with respect to dx minus ae delta t times by alpha times by du over dx integrating with respect to dx, and the final term being ae times by alpha delta t all squared over 2, again integrating with respect to dx. So we can see here that previously these terms I've underlined here were on the other side of the integral, and we've now argued that we can place them outside the integral. If we now perform these integrations, we get the following expression. We get a e L over 2 times by du by dx squared. So the reason we now have an L here is because we were integrating dx with respect to itself, or in this case we are integrating 1 with respect to dx, and because this is a definite integral from 0 to L, the resulting value of x is then replaced by L. Just as an aside, I will show you what I mean by this. The integral of 0 to L with respect to dx is simply then equal to x from 0 to L, which is then equal to L. Doing the same for the other parts of this expression, we get A EL delta t times by alpha du by dx plus the final term A EL alpha delta t squared divided by 2. We can then evaluate using the expression that we derived here for du by dx in equation 16. We can then evaluate du by dx squared so that we can substitute it into equation 17. This is then simply equal to 1 over L squared times by minus ui plus uj squared If we evaluate du by dx squared, we get 1 over L squared times by minus ui plus uj all squared. This is then equal to 1 over L squared, expanding this expression out. Finally, to give 1 over L squared ui squared minus 2 ui uj plus ui squared. If we then put this into equation 17, we end up with another expression for our strain energy, lambda E, this time equal to A E over 2L times by ui squared minus 2ui uj plus ui squared plus A E delta t alpha times by minus ui plus uj, and then the final term A EL alpha delta t squared over 2. And this becomes equation 18. Remembering that the total potential energy, pi, is given by the summation over all the elements for our elastic strain energy, lambda E, from which we subtract all of the work terms, I, then we argued that the displacement ui is found by evaluating the equilibrium. The equilibrium, as you remember, is simply the first derivative of the total potential energy expression. So we can say that equilibrium is then given by partial derivative of the total potential energy with respect to the displacement that we are interested in, and this is simply the summation again over the elements with the derivative of our total potential of our strain energy term divided by the partial with respect to whichever variable we're interested in, which in this case is the ith displacement, from which we then subtract our work terms, again derivatives of these. And we set all of this equal to 0. The final stage then, in order to evaluate our displacements, is to solve this equation, equation 19, for ui. Depending upon the number of unknown displacements that we are looking at, you will get the same number of equilibrium equations that you need to solve.